The Tampa Bay Buccaneers win the Super Bowl 55.
You got
That
me.
means Tom Brady gets his 7th ring.
Well, it's not like the home team's gonna get another ring from the Super Bowl. Uh, yep, we are looking for the moment of inertia for part A of the pendulum of the pivot. As you can see, we are given a moment of inertia for a sphere, which is 2 fifths the mass times radius squared. And yeah, and I forgot to tell you that the parallel axis theorem is basically the sum of all moments of inertia. So as you can see, since we are looking at the pendulum, the moment of inertia, the moment of inertia of the whole system, the mass of the whole system is just m, since apparently the rod is massless, even though it's not really possible in real life. This is a physics class. So from the pivot point, which is from the end of the rod, with the opposite end of the rod where it does not have the ball, the moment of inertia would be the mass of the whole thing, which is just m times the distance squared, and the distance is l, as you can see, and as you can see, the L would stand for the R, the R standing for Raymond, because he takes all the L's. So yeah. Anyways, this should be your total equation for the mass of the mass of the moment of inertia of the whole pendulum about the pivot. So for part B, we are looking for the torque on the pendulum if it is placed from the vertical by angle theta. So as you can see, we have the equation for torque here, which is radius times the force times the sine of theta. We use sine because it's a opposite over hypotenuse. So imagine the leg here, theta's on the opposite side of the leg, and then and uh and that would be the horizontal area at the plane. So yeah, times the hypotenuse. So yeah. So anyways, we can replace F with Sir Isaac Newton's second law, which is mass times acceleration. But the acceleration in this case is g. So I'm not reviving the dead meme. So this is a gravitational force, and R is just L. So it's probably blocked by the watermark, but yeah. So so this is basically your torque for B. So yeah. There's probably far easier ways. You probably put in the I times alpha and did a better job than me. But anyways, there you go. For part C, we are looking for the angular frequency for small displacements, and we have to elaborate. Does depend on m. So as you can see, th this is the Shake-Henmai equation, or the uh simple harmonic motion equation. So but this is the second derivative, aka acceleration, which is actually a, but acceleration is linear acceleration is acceleration angular acceleration times the radius. So the radius in this case is actually L. So yeah, and to find and since we are concerned about small displacements, we have to use something that I don't really like, aka small angle approximations. Basically, the side of theta is approximate to theta, so that's gonna make me cringe so badly. That's gonna keep me up all night. So divide both sides by theta after replacing sine of theta with sine omega t with just theta, and then after that you square root both sides. Let's just ignore the imaginary numbers real quick. So you get the square. So this is what you get. Or this is what I got. So this is the negative square root of acceleration times length divided by theta, or the angle that the pendulum is dangling from its displacement, and that's equal to the frequency. So as you can see, I don't see mass with mass anywhere. So the mass does not. uh, So the angular frequency does not depend on m. There's probably easier ways to do this, but that's how I did it. But anyways, see y'all in the next video. Please drop a dislike. Also, the OBS has been acting weird, so that's why this video was a little late.